Hello everyone and welcome to our final project presentation. We are a team of three people. My name is Jil Ghanshyam Prajapati. Other teammate names is Aryan Hamendra Bhavsar, Manthan Dharmesh Kumar Patel. Today we are going to presenting our work on a deep Q learning for a snake AI and navigate a risk and reward. As a snake AI, you think it's a simple game, but we improve some type of Q learning for the snake AI and we plot some poisons that can change the game. So coming to the next slide. First we face the challenge to simulate the real world complexity and make this a true AI challenge. We introduce a major twist, poison block. This turned a simple pathfinding task into a complex multi-object optimization problem. Our goal was to build a deep queue network agent that learn a trade-off. It must aggressively seek food as a reward while strictly avoiding the poisons as a penalty and a fatal hazard. This is the essence of our complex snake environment. For the next slide, I would like to hand over Aryan Bhavsar.
All right, so thank you, Jill. My name is Aryan, and now I'll explain the methodology for our project. So, we use the state space, which engineered a custom 16-dimensional Boolean vector to give the agent vision of the food, poison, and the obstacles in the game. And we use the DQN model, which is based on the PyTorch library of the Python, which approximates the Q value function to predict long-term rewards. And we also had the reward shaping for our project. Strictly balance the reward penalty structure forces discrimination between the good and bad pixels of the system. And now is the 16 feature state. So our first critical step was designing the state space. Instead of passing the raw images, we engineered a custom 16-dimensional Boolean vector to provide the agent with all necessary information. And this vector includes the danger in three directions: the direction of the food, and crucially four inputs specifically for the direction of the poison. So this guarantees the AI has the necessary vision to differentiate between the good and bad targets. And for the network itself, we upgraded the architecture to be deeper than a standard tutorial. So this is input vector representation which we used, and now it's on the neural architecture. So we used our model uses of a 16 neuron input layer, two hidden layers of 512 and 256 neurons, and an output layer of the three actions, which contains actions like left, straight, and right. Now, like the reward system for our project. So the learning is driven by a carefully balanced reward function. So we need the agent to prioritize safety rather than just going for the rewards. So we set the reward for eating food at a positive plus 10, but the penalty for eating poison is a severe minus 50, which can lead to massive penalty forces the network to design a low Q value to any action that involves risks, training it to prioritize avoiding the purple blocks over reaching the food quickly. So this massive penalty can be accidentally learn. It's okay to like can train the agent to not choose, it's okay to eat poison if the food is close too close. So that's why we keep it more than the usual rewards, negative rewards for the rewards of this agent. Now on to Manthan for explaining the further explanation of the presentation and the uh, demo of the whole project. So now over to Manthan. Thank you.
Thank you, Aryan. Now let's see the project in action. I am running our main.py file, which is divided into three decent spaces. Phase 1 is the baseline agent. This represents a naive AI knows nothing about the poison. As you can see, phase 2 is the training phase. Our DQN agent is now playing 200 episodes in the terminal. During this time, it is using our memory buffer experience and reply to maximize its Q values based on the plus 10 foods rewards and the minus 50 poisons penalty. Phase 3 is the train agent. Finally, watch how to our fully trained agent behaves. It sees like a proper position and activity navigates around it to get to the red food. The agent has successfully learned the difference between the high rewards item and critical high penalty items. This graph shows our learning curves. Notice the high variance at the beginning. That's the agent exploring randomly. But by episode 150, the score dramatically stabilized as the agent coverage on the optimal policy, providing the network has learned the complex risk versus rewards calculations. Now over to Aryan explain about the conclusion and about the final results. Thank you.
All right. Thank you, Manthan. So, as we all see, the final project run, like the demo of the project and the final output of the learning curve, as Manthan explained very perfectly about the whole project. So, basically, it's like that the phase one is the baseline of the project, like the normal game without any AI included in it. So it only avoids walls. It treats poison blocks as empty space because it has no concept of hazard types on uh, on its coding or on the way it thinks, because doesn't think the poison as a hazard for itself. So it's basically blind to the poison. And as we did the phase two, like phase two was the training phase, like 200 episodes. We trained the agent for 200 episodes, and after training the agents, the phase three was the whole network, the train agent. So it has learned that the poison input correlates with the massive penalty of the minus 50. So it actively pathfinds around the hazard. So now as we see the phase 3, it's trained DQN, the train network, so which sees the hazards as a big danger for itself, because it can get it to minus 50 points. Rather than just eating food and getting plus 10 points, it can get to minus 50. So after doing that, it actively pathfinds around the hazards to make its way to the food. And so that's how we trained our model using AI. So it has the poison awareness in the system. So that's how we found success in the system.
To summarize our project, we successfully transformed a simple arcade game into a complex decision making task. The agent learned not just to pathfinding but to weight risks against reward in a real time. By carefully engineering the state space, design a deep neural network, and applying a harsh reward structure, our agent learned not just to pathfinding but to weight risk and against the reward in a real time. I hope we contribute a certain point that the guys you can learn, and this project demonstrates the power of deep reinforcement learning in solving a non-trivial multi-object problems. Thank you for watching. We are now open for any questions you might have. Thank you.